Today, we're cracking open a piece of technology that feels like straight-up magic, but is actually the result of some incredible and honestly, surprisingly recent breakthroughs. We're talking about machine translation. You've definitely used it, right? You type something in and bam, it just appears in another language, almost instantly. But how does a machine actually go from a jumble of words in English to a perfectly structured sentence in, say, Japanese? How does that even work? Well, let's break it down. For the longest time, the answer was, well, it was incredibly complicated. Before about 2014, machine translation was a completely different beast. Just imagine trying to teach a computer every single grammar rule for English. Then do the same for Romanian. And then you have to write a master rule book on how to connect the two. For every single pair of languages. It took a huge amount of human effort and deep linguistic expertise, and it created this fragile, complex web for every translation. But then, a new idea came along that just completely changed the game. It was so much simpler, more elegant, and way, way more powerful. It's called the encoder-decoder model. It's a really simple two-step process. First, an encoder network reads the English sentence and basically squishes its entire meaning into a list of numbers, what they call a single thought vector. Then, a decoder network takes that vector and unpacks it, word by word, into the new language. You can think of it like summarizing a message for a friend, who then has to reconstruct the whole thing in their own words. And this implies something pretty incredible. That thought vector, it's basically a new language, not for people, but a universal language of meaning that the machine creates for itself to bridge any two human languages, a machine interlingua. Kind of mind blow, right? So this new method was super powerful, but it created a whole new problem. If the machine is learning all on its own, how do we tell it when it's doing a good job versus a bad one? We needed a way to score its translations automatically. And this led to a really clever yardstick for measuring quality that's still the standard today, the BLUE score. BLUE is, at its heart, a wonderfully simple idea. It just measures how many of the words in the machine's translation also show up in a professional human translation. The more overlap you have, the better the score. So let's look at an example. The machine says, the feline sits on the mat. The human reference is, there's a cat on the mat. Okay, so the words the, on, and mat match up. That's 3 matching words out of 6 total words in the machine's sentence. So its score is 3 out of 6. Simple as that. But you can probably already see a problem here, right? What if a clever but kind of lazy translation system tries to game this simple overlap score? Okay, here's how BLUE solves that. If the reference is the cat is on the mat, a lazy machine could just say the 6 times and get a perfect naive score. But BLUE is smarter. It clips the count. Since the word the only appears twice in the human translation, the machine only gets credit for it twice. So its real score is a much more honest 2 out of 6. No cheating allowed. So we had a powerful new model and a way to measure it. But this early encoder-decoder approach, it had a critical weakness, a real fundamental bottleneck. This quote from a 2015 paper by Vauquois and his team just frames the problem perfectly. That single thought vector we talked about had to contain the entire meaning of the source sentence, no matter how long or complex it was. Imagine trying to memorize a long, complicated paragraph, but you're only allowed to write down a 10-word summary. You're going to lose a lot of important details, right? That's exactly what was happening here. The model really struggled with long sentences because that single vector just wasn't big enough to hold all the necessary information. Now, researchers came up with some pretty ingenious patches. One 2014 paper found that simply reversing the order of the words in the input sentence actually made things better. It gave the decoder a slightly better jumping off point, but it was just a trick. It didn't fix the fundamental memory problem. The real solution was another revolutionary idea, a concept that would go on to basically define modern AI. It's called attention. The idea is just beautiful. Instead of forcing the decoder to work from one static, compressed memory of the whole sentence, what if we let it look back at the original text? What if, for every single word it generates, it can ask, hey, which of the original words are most important for me right now? And that is the attention mechanism. It's a dynamic process. As the decoder builds the new sentence, it creates a custom-weighted summary of the input for each step. When it's translating a noun, it can pay more attention to the original noun. When it's working on a verb, it focuses on the original verb. It can look wherever it needs to, whenever it needs to. And the impact?
Oh, it was staggering. The 2015 paper that introduced this idea reported a 50% relative improvement in BLEU score over the old method. It didn't just fix the memory bottleneck, it blew it wide open.
This one single breakthrough, attention, directly paved the way for the AI we all use today. In fact, the pace of innovation from this point on was just breathtaking.
The story unfolds so quickly. In 2014, the sequence-to-sequence model appears. Just 1 year later, in 2015, attention solves its biggest weakness. Then, in 2017, there's this big realization. Attention was so powerful, you could get rid of the old step-by-step processing units entirely. This idea created the transformer, the architecture behind pretty much every large language model we have today.
Essentially, attention just completely took over. Those old, clunky processors for encoding and decoding were replaced entirely by more powerful attention mechanisms. It turned out that the catchy paper title, "Attention is All You Need," wasn't some exaggeration, it was a roadmap to the future.
Which brings us right back to where we started. That simple act of translation on your phone is powered by all these layers of breakthroughs. It all started with a simple idea of encoding and decoding, which led to machines creating their own internal language of meaning, and was perfected when we gave them the ability to pay attention. It really makes you wonder, what comes next?